Doing all right. I wanted to ask y'all about your thoughts on the test. I know we're scheduled to have it Thursday. Does anyone see a problem with moving it to Tuesday? Would that hurt your feelings? Give us more time to catch up, give you more time to complete the homework and the quiz. That way the material's not rushed, because honestly, the material in 4.9 is super important as we move forward, especially if you're going to go on to Calc 2. So we need to take our time with that. I don't want to rush through that. But that means that somewhere in Chapter 5, we would have, what, 4? I think that would give us only 4 days. Somewhere in Chapter 5, we're going to have to compensate. Because then that would give us 3 days to finish all of Chapter 5 and 6.2, plus a review. Yeah, Chapter 5 is on the final.
Oh.
It's just that, I'll just have to figure out, because I know in my mind what's important. Some of the stuff is kind of tedious, and from a foundation standpoint, it's important. But anyhow, if we do move the test back to next Tuesday, then Chapter 5 we might have to reconfigure. Okay, then. We'll do that test to next Tuesday.
You're moving it?
Yeah.
Hell yeah.
That would be the 23rd.
Oh.
I hope that helps at all. I know it's definitely not ideal, but neither was missing a class, so. Okay, with that in mind, let's then hold off on any homework questions until next class. That way we can cover this content and then talk about next class. We can maybe finish 4.9, discuss what's on the exam, and then any questions about homework on Thursday.
So that's all the due dates too, as well?
Yeah, I'll change the due dates for you, for the homeworks and the quizzes. Okay. So then, back to 4.7. With L'Hopital's rule, this is our last indeterminate form. We're one of these three. But they're kind of all lumped together because the process to evaluate limits of those forms is the same. Okay, and we sort of abstractly walk through the idea of how we compute those limits. If we evaluate a limit directly and we get one of those three forms, then it's crucial to rewrite the function f of x to the g of x as e to the g of x times the ln of f of x. So that's the inverse property of natural log in e. And then we're using the logarithmic property to pull the power of g of x down front to multiply the natural log. Okay, so then we're evaluating the limit as x goes to a on e to the g of x times the ln of f of x, and it doesn't affect e, so what we're able to do is move that limit here in this step. We're able to move the limit up into the power and just compute the limit and say whatever our answer is, it's e to that power. Okay. So this limit here, the g of x times the ln of f of x, if you have one of those forms, will always be the 0 times infinity form, in which case we need to rewrite it in this step, and then use L'Hopital's to compute that limit, call it L, and then the overall limit, as we said, is e to that power, e to the L. So just get it in your mind whenever you get the form 1 to the infinity, 0 to the 0, infinity to the 0, in terms of a limit, that your answer will always involve e to a power. So I know that's a bit abstract, like I said. We'll look at a couple of examples. For those of you that came in late, we're moving our test to next Tuesday, not Thursday. So the test will be on the 23rd. Okay. Looking at this stuff, does anyone have any questions or comments initially? It looks a bit messy, but we'll look at some examples and hopefully clarify any questions you have. This by far is the most involved of the indeterminate forms when we're using L'Hopital's rule. Okay, so we'll start off with we'll start off with the most simple case, which is x to the x. So we're going to compute the limit as x approaches 0 from the right on the function x to the x. And really just like the key with any limit is to determine, first of all, what are you actually working with? What does that limit evaluate to? Is it something I can evaluate immediately? Is it something that is akin to chapter 2 where we computed the limits at infinity or infinite limits? Or is it something different? All right. All right, let's try this. Does this work? That's so weird. I'm gonna try something that's gonna bother me if I have to walk over here and change stuff. I don't know that that's gonna make a difference, but let's see. All right, whatever, we'll do our best. So direct substitution, of course, gives us 0 to the 0. So then we have to default to the process of evaluating limit of the form 0 to the 0. So the first thing to do is, now we know that it's of that form, we have to rewrite x to the x as e to the x times the natural log of x. So then we're, instead of computing the limit as x approaches 0 from the right on x to the x, we're computing the limit as x approaches 0 from the right on e to the x times natural log of x. Is everybody okay with that step? Any questions? Again, the limit as x goes to 0 doesn't affect the e, it only affects the power. So this is equivalent to computing, why is it blue? Equivalent to computing the, e to the limit power. Sorry, habit. So that's always step one when you get limits of that form. We rewrite them. And then when we evaluate the limit up here in the power of e, like I said, it's always going to be a form of 0 times infinity, which is, it takes us back to that first indeterminate form that was related to L'Hopital's, where we had to look at taking one of the factors and dividing by its reciprocal. Do y'all remember that process? So that's what we're going to have to do here. Does this work? Okay, that works. I'm just going to leave a little bit of space And sort of, kind of as an aside, we're going to compute this limit. Down here. You might remember we did compute that limit already, but it's a reminder of the process. So it's kind of like now we're starting over with this new limit. So we're just going to evaluate this new limit, and then whatever we get for this result, we're going to take e to that power, and that's going to be our answer. So starting over, directly substituting into this limit, x is going to 0, so we have that factor is 0, and then this is the ln of 0 from the right, which is negative infinity. So now we're going back to that first related indeterminate form, and in order to evaluate this, we have to rewrite this. ln of x divided by 1 over x. So notice that we have not applied L'Hopital's rule at all so far. We're going to check that this limit, the quotient we have here, is either infinity over infinity or 0 over 0 before we apply L'Hopital's rule. So remember, it has to be one or the other before you apply L'Hopital's rule. So x is going to 0, the numerator approaching negative infinity, the denominator is approaching what? What does 1 over x approach as x approaches 0? Infinity. Okay. So now and only now are we going to apply L'Hopital's rule to that ln of x over 1 over x. Do you all have any questions? Make sense? Okay then. So now by L'Hopital's rule, computing the same limit, but we look at the derivative of the numerator divided by the derivative of the denominator What do we do next after we apply L'Hopital's rule? Yeah, you have to simplify that. So L'Hopital's rule, simplify, then reevaluate. That's always the process when you apply L'Hopital's rule. So we're simplifying algebraically. And that gives us what? Yeah, limit as x goes to 0 from the approaches 0 from the right, and then this simplifies to just negative x. So the limit there is 0. Anybody have any questions on that? We're not completely done yet. Remember, that's the limit of x ln x. And that was this limit here. So your final result is e to that power. Which is 1. So that's your final answer. Which means on the function x to the x, as we approach 0 from the right, the y values approach 1. So we're approaching a finite number, x values are approaching a finite number rather, and the y values are approaching a finite number, which means that on the graph of x to the x, you have a hole at 0, 1. kind of like two processes built into one when you encounter these three indeterminate forms. It always involves you first rewriting, and then when you evaluate the limit, it's always going to be 0 times infinity, which means you have to involve the reciprocal of one of the functions. You get that limit, and then you raise e to that power, and that's your answer to the original limit. Does anyone have any questions?
So how do you, I'm just kind of confused how you are able to figure out where the hole is. I know it's, 0, 1, but how do you know that was a hole though?
Well, so the idea of a removable discontinuity is that as x approaches something, a finite number, the y values also approach a finite number. If it were a vertical asymptote, we approach a finite number, the y values would always approach infinity or negative infinity. Right, so maybe if you just thought about it like visually, like if whatever this hole is in this graph, as we approach that value, the y values do approach something specific here. But if it's the case where we're approaching this finite number, a, it's an a, from the left or from the right, and the function values get bigger and bigger, then that has to be a vertical asymptote there. So since it's a finite number, it's a hole in the graph. Does that make sense?
Yeah, no, I'm just kind of wondering, I know the logic to this, but when it comes to, does, for the graph of x to the x, when it comes to 0 over 0, and that, is there already a hole there, or?
Well, it depends. It really depends on what that limit comes out to be. The whole thing with any of these indeterminate forms is that, for instance, 0 to the 0 or 1 to the infinity, those could have any value. And that's why we call them indeterminate. Because initially on the surface, we're not able to determine their value. They can take on any value. It's only through the process that we're applying that we're able to determine, does it have an actual value, like 1 or infinity or negative 12 or
So
whatever.
0 over 0, or 0 to the power of 0 does not have a value?
In the sense of a limit, yeah.
Okay, all right.
So either one we look at, it's the same function. I don't know if this will tell us, but notice this says it's the point 0, 1. But we know that's there's an actual hole there. I wouldn't have you graph these, but it's, with a lot of times when you compute a limit, it's important to know what that's actually telling you about a function. We saw in some instances, it didn't really matter. We were just computing a limit, right? But like in section 4.4, when we were actually graphing, it's important to know like what's happening at various locations. So I wouldn't have you graph something like that. On the exam, I'm just looking for the limit, really. Do y'all have any other questions on that example? Yeah.
Can you get infinity as an answer since you just continuously take the derivative over and over again until you get a number?
Yeah, it's possible. I don't recall when I've seen that recently. So for us, these things will always, all of the examples that I've seen are finite.
Okay.
I'm going to try to reopen this and see if it works. Any other questions on that? Okay, so why don't you all try this one? It's in your handout, right? Okay.
Oh, this is just.
Oh, oh, so that's not this, that's.
Yeah, that's right.
Oh, oh, okay.
Just the one over there.
Okay.
This entire stuff over here, which is natural life one is just 0. You know, the execution over here, the common is just 0. Approaching 0.
Yeah, so that's the derivative of the inside, is the derivative of the exposure one. Yeah, you would change Yeah, right. So then I did 1 over the argument times the derivative of, which is that.
And then we got that. Is that right, or how should I structure that?
So that's fine. I think it would be a little bit easier if you let the derivative of this just be this representation. Because you'll notice we have that.
Yeah, I just realized that.
Yeah.
Darn, that's good to know.
Yeah, kind of working on the thing, but looking
I
ahead.
know, I always go to simplifying things, and then if I do that, then I'm not gonna get anywhere, right?
Yeah.
Because those things are gonna cancel.
Yeah, right. You're welcome.
So if we're simplifying this, don't simplify this, we can just go up here and change this and that.
Okay, I think everybody made it that far, at least. Most of you further, but. So we're evaluating the limit as x approaches infinity. By the way, when we do that for any function, what is that going to tell us? Limit at infinity tells us,
Horizontal
yeah,
asymptote.
horizontal asymptotes in behavior. So we're computing this limit. So honestly, I'd recommend just taking that aside, not trying to compute it, you know, as it is up there with e to that power. If it's more conducive for you not to forget that it's e to that power, then feel free to work that way. But it might be a little bit more clean if we work it out this way. So x is going to infinity, the first factor is infinity, times, we've got the ln of 1 plus a thing approaching 0. So that's infinity times the ln of 1, which is infinity times 0. So I believe most everyone was able to rewrite this. Dividing by the reciprocal of x. And reevaluating that limit, we see that that's now of the form that L'Hopital's applies to. So that's 0 over 0. Don't forget now, when we take the derivative, especially the derivative of the top, that it's a chain rule. The outer function is the natural log. So when we take the derivative, we have 1 over the argument times the derivative of the argument, which is -1 over x squared. taking the derivative of 1 plus 1 over x. Okay, are there any questions on that? Okay, look at our limit here. So x goes to infinity. Divided by the derivative of the denominator, which is also negative 1 over x squared. So I would write out the derivative of the numerator and denominator explicitly as they are before I started thinking about simplifying. Because if you're trying to simplify just the numerator, you're going to multiply the x squared in through the denominator, and it's going to get absorbed and lost. If we just write out the derivative of the top over the derivative of the bottom, then we can have a bigger picture of what's happening. If, for instance, these two factors of negative 1 over x, the terms negative 1 over x squared didn't cancel, then probably be a good time to either try multiplying through on top, or whatever the denominator is, especially if it's a fraction, multiplying by the reciprocal on top and bottom. But as it stands here, it's super easy to simplify. Because those two factors divide away, and all we're left with is this. So as x goes to infinity, this term here approaches 0, and we just end up with 1 over 1, which is 1. So the limit on the power of e is 1, therefore our final result, go back up here, is equal to e to the first, or e. Does anyone have any questions about that example? If I need to scroll down or anything, let me know. Okay, I'll just put an asterisk here. That's not good. We did down here. Okay, so the in behavior of that function, and maybe you've seen e defined that way before, but often that limit definition, as x approaches infinity, 1 plus 1 over x to the x, often that is a definition of e. Maybe in algebra textbooks you might see that, but really without the context of L'Hopital's rule, you have no way to justify that limit is actually e. So here's our 1 plus 1 over x to the x. We said that as x approaches 0, that should describe the end behavior, or the horizontal asymptote. So we can see out towards positive infinity, the function is approaching that line. Y equals to e. Everybody okay with that? All right. think we'll leave 4.7 there if there aren't any questions. Next class, I'm more than happy to answer any homework questions that may arise, but I think we've at least got a good sense of how these problems are done. Well, actually, no, there's this last example I wanted to mention from your homework, my bad. 4.7, number 22 in the homework. So there are instances, like this is an example of showing that L'Hopital's rule fails for this limit. And then it says, find another method to evaluate this limit. So it's x approaching infinity, root ax plus b over root cx plus d. And we see that if we directly substitute in for that limit, what would our limit approach? What?
Infinity over infinity?
Right, yeah. Numerator a times infinity plus b is infinity, or if you will, the square root of infinity over the square root of infinity, which is infinity over infinity. Okay, so then say, well, infinity over infinity is something L'Hopital's rule applies to, so let's just apply L'Hopital's rule and see what happens. Okay, so derivative of the numerator, we're going to compute the derivative of the ax plus b to the 1/2. And this is our process that we're applying L'Hopital's rule, and we're going to look at what that is. It's going to show us why L'Hopital's rule fails. So what's the derivative of ax plus b to the 1/2?
Ax plus b to the
Is that it?
No, it's times A.
Yeah, times the derivative of the inside function. Derivative of ax is a, derivative of b is 0 because it's a constant. So we've got a over 2 times the root of ax plus b. As the derivative of the numerator. So then what would the derivative of the denominator be?
c over 2 root of the expression.
Yeah, great. Now, before we reevaluate, what do we need to do? L'Hopital's rule, then we simplify. So we're going to simplify all of this now. What does that simplify to? Yeah, the 2's will divide out. So we're just going to invert the denominator, multiply top and bottom, so the denominator is 1. So we're basically simplifying this way. If you need to see it this way, we're going to say 2 root cx plus d over c up here and here. So the 2's divide out. What we're left with is a times the root cx plus d over c c times root ax plus b. But keep in mind, if we apply L'Hopital's rule again, we're going to take the derivative of these roots and have this same sort of structure as long as we keep applying L'Hopital's rule. And notice L'Hopital's simplify, we evaluate the limit, we still come up with infinity over infinity. So I believe your homework has you compute another L'Hopital's rule, but I'm just going to stop here because what happens is you keep ending up with infinity over infinity. No matter how many times you apply L'Hopital's rule, you still get something that's indeterminate. So L'Hopital's rule doesn't help us determine the value of this limit. I'll just make that note. If we keep applying, if L'Hopital's is applied again and again, etc., we still end up with a limit that's infinity over infinity. That is, L'Hopital's rule does not help us here. So that's why it says show L'Hopital's fails. We've showed it's failed. We have shown it has failed. And then therefore we need to come up with a different way to evaluate that limit. Does that make sense? If you want, I think you'll have to do another round in your homework just to see that it ends up in the same format. Okay, so then we go back to the original limit. What's another way to compute that limit?
Multiply with the conjugate.
So we could try to conjugate the denominator. That's particularly helpful if we end up with like a 0 on the bottom. If we're trying to cancel that the factor of whatever's giving us a 0 on the bottom away, then typically the conjugate is the go-to. That's not the case here because we end up with a large number over a large number. It's not something that's undefined. So then you kind of have to think, you have to dig deep here. The limit on the root, first of all, can we rewrite the radical ax plus b over cx plus d as one radical? Can we rewrite it like this? Is that valid? Yeah, that's just an algebra step. Particularly the idea of continuity, when the limit can get passed into the root, when the inside function, ax plus b over cx plus d, is continuous at that x value, which it certainly is. Because we're just thinking about x getting larger and larger and larger. A, b, c, and d are positive. There's nothing weird happening there. So we're passing the limit into the square root. So ultimately, all we're doing is computing the limit on a rational type function, ax plus b over cx plus d. As x goes to infinity, that limit is what? I ask you to compute the limit as x goes to infinity on 2x squared plus 4x over x squared minus 1, what would that limit be? 2. 2 over 1, right? Leading term over leading term.
So A over C?
So A over C, right? Leading term over leading term here. AX over CX, the x's divide out. So that's some finite number, the square root of something divided by something else is the answer to that limit. But using L'Hopital's rule, you would have never gotten to that result. So that example is showing that in the instance L'Hopital's rule fails, it does not mean that the limit doesn't exist or that we can't evaluate it. There's always another way to evaluate. Do y'all have any questions on that? Okay, for real now, that's the end of 4.7. So 4.9 may not seem like it's related to anything that we're doing in chapter 4. A lot of times people will choose to put this with chapter 5, but really chapter 4 was what derivatives tell us. So we'll see in a moment how we can relate what we're talking about in 4.9 with the notion of an antiderivative back to the derivative, or back to things we already know about. So in chapter 3, the idea was if you were given a function, it would say find the derivative of that function. Here in 4.9, we're still given a function, but now we're thinking of the reverse process. Instead of find the derivative of this function, it says find the function whose derivative is the given function. Not take the derivative, find the function whose derivative I take to get the given function. Okay? And we call that process an antiderivative. So given a function, find another function we'll call capital F of x for now, whose derivative is f of x. And so an example of that, let me close this and reopen it. I didn't do the thing. So for example, find the antiderivative of the function 2x. So we're going to call the antiderivative capital F of x for now. And I'm just going to write this out in words. The antiderivative is the function that we take the derivative of in order to get f of x equals 2x. So what function, when I take its derivative, do I get 2x? X squared. So there's the antiderivative of the function 2x. So notice we're still thinking about derivatives, but we're just kind of thinking about what do I start with in order to get that derivative, as opposed to just taking a derivative.
Aren't there multiple answers for something?
Yeah, there are multiple answers. So the nice thing with, I guess the nice thing with derivatives is there's always a formula to find a derivative, right? If you look at a function, you say, well, that's a quotient, I apply the quotient rule, there's my derivative. But there really wasn't a good way to check, did I actually take the derivative correctly? Do I have the right derivative? With the process of finding the antiderivative, there's not one explicit formula. So finding an antiderivative in general is a very difficult thing to do. However, once you've found the antiderivative, you can always check if the antiderivative is correct. So it's a harder process, but you can check your work, whereas the derivatives are an easier, more straightforward process, but you can't check your work. So there's kind of the trade-off. Yeah, so if I'm claiming my antiderivative is x squared, the way I check that is just take the derivative. So I'm going to take the derivative of f, capital F.
What if it was like x squared plus 3, because then the constant would have been 0.
Right, yeah, so we have yet to talk about that, but it's a good point. So the question was, well, what if there's a constant in there? Like, what if it were x squared plus 5? Wouldn't it have the same derivative? The derivative of x squared plus 5 is still 2x. Or x squared minus 5,000, the derivative is still 2x, right? So the derivatives were unique up to a constant. So we'll talk about that in a minute. But essentially what it boils down to is that every antiderivative you take will have a plus c attached to it, because the derivative of any constant is 0. I don't know if I put the definition. Sorry. I didn't put the definition, but the definition of an oh yeah, I did. The definition of the antiderivative is sort of formulated in terms of this checking process that we have. In order for a function to be an antiderivative, capital F, then capital F prime must be the original function. So that check is kind of built into the definition. A function, capital F, that's the thing we find. So that's the antiderivative. So the last part of that sentence says that the derivative of the antiderivative is the function itself. So when we write that, that's the derivative, or if you want to see it in a different notation, that's the derivative of the antiderivative is the function. So really in a more, I guess, simplistic sense, what does that mean about the derivative and the antiderivative? If the derivative of the antiderivative is the function itself.
Just reversing the process.
Right, it's reversing the process, and the correct term for that is what? not reciprocal, the inverse, yeah. So this is like the square of the square root gives you back the input or the function, right? So the derivative and the antiderivative, the process of taking a derivative versus the process of taking the antiderivative is, they're inverse operations or inverse processes of one another. Yeah, I mean, there's a caveat, a little caveat to this, but by and large, that's kind of what we're dealing with. Okay. Do y'all have any questions on that? So that's just from the definition that we read into the definition a little more. Okay, so we'll look at some more functions. Given f of x, find the antiderivative. In other words, what function do we take the derivative of to get 1? Yeah. And so this is where the knowledge of derivatives is super helpful. If I take the derivative of x, the derivative of x is 1. Therefore, the antiderivative is x. Does that make sense? Not all of these, but when you check, you're just checking, does the derivative of that capital F you found, does that actually equal to the given function? So that's how you can check these. Before we get too far into this, though, we'll present, I think it's presented as a theorem, I'm not sure, but just note here that if we say the antiderivative of 1 is x, really it's 1 plus any number is the actual antiderivative. Because once we take the derivative of this constant, it's 0, the derivative of x is 1. So all of your antiderivatives should have a plus c for a constant. It's any real number. Is that clear why? Does anyone have any questions on that? So the derivative of this function is 1 no matter what, because the derivative of a constant is 0. How about the antiderivative of cosine? Sine x. What function do we take the derivative of in order to get cosine? So our antiderivative, sine of x plus any constant, or minus any constant.
Does it matter if you put a minus or a plus? Like, how would you?
No, usually it's plus c, but it's minus. It's minus. It's fraction. It's whatever. But usually the convention is just at plus c. So the antiderivative of cosine is sine. What's the antiderivative of sine?
Negative cosine.
Negative cosine. Do y'all agree? Negative cosine. If I take the derivative of negative cosine, I should get sine. Anyone have any questions at this point? Yeah.
For like the tests and stuff, will those be written as f prime of x so that we can tell?
No, it'll just say, we'll talk about the notation in a little bit, but the instructions are find the antiderivative. So you're
Okay.
given that function. There won't be any primes.
Okay.
How about 1 over 2 root x? What's the antiderivative of 1 over 2 root x? Square root of x. Do you all agree? Hopefully you've done that one 50 times at least. Okay. How about 1 over 1 plus x squared? What's the antiderivative of 1 over 1 plus x squared? On the right track.
First tangent of x plus c.
Yeah. It's this one's, I know we kind of glanced over inverse trig functions, but this one is inverse tangent of x. If you're going on to Calc 2, that's a really common antiderivative, so you should know that one. I'm going to add one more example as another very common antiderivative in Calc 2. Okay, so find the antiderivative of 1 over the square root of 1 minus x squared. Close. Nope. Nope. Nope.
It's inverse sine of
It's inverse sine of x, not sine of x. Two totally different functions. Inverse sine of x. So honestly, those two, as far as the inverse trig functions go, are by far the most common antiderivatives you encounter for inverse trig functions. If you're going on, certainly need to know those. Okay. So that's a good reminder of the derivative of inverse sine is this, the derivative of inverse tangent is that. Now you remember. Are there any questions? So let's see, we'll take a break and then talk about the notation for the antiderivative. Okay, so let's talk about the notation moving forward for the antiderivative. It won't be, the instructions typically don't say, maybe when you first start out, but instead of find the antiderivative of f of x, our notation is going to be this elongated s with f of x and a dx. So we'll see in chapter 5 what the elongated s means and where that dx comes from. But the dx basically tells us that when we took the derivative with respect to x, or take the derivative with respect to t, that dx tells us we're finding the antiderivative with respect to that variable. So our dx find the antiderivative. Well, I won't say that, because really the find the antiderivative part isn't what the dx is telling us. The dx is just telling us with respect to. The elongated s is for the antiderivative. I'm just abbreviating antiderivative. So that's our notation for finding an antiderivative moving forward. Let's look at more examples. We have the antiderivative of 4x cubed with respect to x. It's the same question still, though, however. What function do I take the derivative of in order to get 4x cubed? X to the fourth. Do y'all agree? Plus our constant. So the derivative of x to the fourth is 4x cubed. So the antiderivative of 4x cubed is x to the fourth. Make sense? Okay. How about the antiderivative of negative 1 over x squared with respect to x?
Over X.
We saw that one previous section. 1 over x. What do y'all think? Derivative of 1 over x is negative 1 over x squared. Yeah. Ultimately, what we're building up to is sort of eliminating the guesswork out of it, because more often than not, you're looking at a function where it's not clear what the antiderivative is. So really, there's a lot of buildup in Chapter 5, but primarily the integration or the antiderivative technique that we come up with in Chapter 5 is a substitution technique. The other techniques you learn in Calculus 2. So we do eliminate some of the guesswork out of all of this, but really the foundation, the fundamental functions that we've seen, trig functions, inverse trig functions, logarithms, exponentials, you really should know those derivatives, which means you know the antiderivatives. Okay, how about the antiderivative of negative sign with respect to x? Derivative of cosine is negative sine. So the antiderivative of negative sine is cosine plus constant. Okay, what's the antiderivative of e to the x with respect to x? Right, the derivative of e to the x is e to the x. How about the antiderivative of secant squared with respect to x? Tangent is the derivative of tangent secant squared. Do y'all agree? Not sure?
Isn't it secant x tan x?
Okay, so the derivative of what gives us secant tangent?
Secant?
Derivative of secant is secant tangent. So since we mentioned that, the antiderivative of secant tangent with respect to x would give us secant. So, all of these, what we're looking at is going this way, that's the antiderivative. Going this way is the derivative. couple more that are maybe a little bit more involved. How about the antiderivative of 3 times e to the 3x with respect to x? Okay, e to the 3x. So do y'all agree, is the derivative of e to the 3x 3e to the 3x? Yep. Antiderivative is e to the 3x. Okay, so what's the antiderivative of then 4 cosine of 4x with respect to x?
Wouldn't it just be sine of 4x?
Is it sine of 4x?
The derivative of the other?
So here we go, let's check. Our claim is that the antiderivative is the sine of 4x plus c. So what we're checking is the derivative of that function equal to the given function, which we'll call lowercase f of x, that is the derivative of sine 4x plus c equal to 4 cosine 4x. So we can just check our work. What's the derivative of, what's the derivative of sine 4x plus c? Derivative of sine is cosine.
Times the derivative of 4x, which is 4, so it gives you 4 cosine
Right.
4x.
Times the derivative of the inside. Which is 4 cosine 4x. So the antiderivative of 4 cosine 4x is sine 4x. Do y'all have any questions? Okay, example 9. What's the antiderivative of 1 over x with respect to x?
ln x.
So is the derivative of the natural log of x 1 over x? So the antiderivative of 1 over x is the natural log of x. So you may or may not remember us talking about the derivative of the natural log of x is 1 over x, but also the derivative of the natural log of the absolute value of x is also 1 over x. So that's how we want to think about the antiderivative of 1 over x as ln of absolute value of x. The reason for that is because they have the same derivative. The derivative of the ln of x is 1 over x, and the derivative of the natural log of the absolute value is also 1 over x. So the reason we're working with the absolute value here, the antiderivative, and we really didn't do much with the derivative, is just so that we can sort of extend the domain of our antiderivative. Okay, because if we just said, if we looked at the function 1 over x, we see that it includes everything but 0. And if we just said that the antiderivative was the natural log of x, we would be including all positive numbers that aren't 0. But if we looked at the absolute value, then we can put negative numbers in for the input. I don't know if that's clarifies, but it's just so we can have more inputs into the antiderivative. Okay, let's stop there. Any questions? Oh, we already did those. Yeah, we did most of those. This example 6, what's the antiderivative of that function?
Inverse sine.
Inverse sine, yeah. Inverse sine of x. We'll just remind ourselves again with that one. Sorry, my notes are kind of mixed up. So finding an antiderivative from a known derivative. I'll give you a formula sheet for this section that has all of the basic antiderivatives on there. Ultimately, you should know all of those because ultimately we should know the derivatives of all of these functions. But the idea is that maybe I forget the antiderivative. We can always kind of reverse engineer the formula for an antiderivative just by knowing the derivative. So we'll look at a few examples of that. Let's say I know. Let's say I take the derivative of the function e to the 3x. And I know the derivative of that function is 3e to the 3x. So if you know the derivative, you know an antiderivative. What we stated earlier, just by the definition of an antiderivative, it is the reverse or the inverse process of the derivative. So let's say I know this fact, then what happens if I take the antiderivative with respect to x on both sides of my equation? It's just a little bit more symbolic than what we've written out. But when I take the antiderivative of a derivative, what happens? Yeah, you just get the function, right? This is like squaring a square root. So the antiderivative with respect to x and the derivative with respect to x just cancel each other out or undo what the other did. So we just end up with 3x on the left-hand side equals to the antiderivative of 3e to the 3x. So now what we ended up, from the derivative, what we ended up with, as we saw in our first few examples, is a formula for the antiderivative of something. Now, another way we could look at this is where we have this constant of 3. So I could divide both sides of this equation by 3 and say 1/3 e to the 3x is the antiderivative of e to the 3x. Just divide by 3 on both sides. So maybe that, yet again shows us that they are kind of reverse processes of each other, right? If I say take the derivative of e to the 3x, you say it's e to the 3x multiplied by 3, but the antiderivative of e to the 3x is still e to the 3x divided by 3. It's reverse process of the derivative. Okay. Does that process make sense? Okay, what questions do you have?
130.
Well, we just divide this side, we divide this by 3,
Oh,
and then we divide this by 3.
I ran back.
So when you see the formulas for the antiderivatives, they always have these, like, they have an A there instead. So that was a specific example. A more generic example would be to take the derivative of e to the ax, where a is a real number. The derivative of e to the ax is a times e to the ax. So then we know the antiderivative. If I take the antiderivative of both sides with respect to x, again, the antiderivative with respect to x and the derivative with respect to x on the left-hand side undo each other. We have e to the ax on the left is the antiderivative of a e to the ax and then if we divide both sides by a, we have an antiderivative formula for e to any power times x, or e to the ax. So divide both sides by a, we have e to the ax over a as the antiderivative of e to the ax. So that is one formula on your formula sheet. But notice we really only need to know two things, the derivative and the fact that the antiderivative and the derivative undo each other. So you start with a derivative equation, you take an antiderivative, now you have a formula for an antiderivative. Any questions about that? And it works for any known antiderivative. This process we could just look at maybe one more. Let's look at taking the derivative of, I don't know, let's say the sine of a times x. What's the derivative of the sine of ax?
A cosine x.
Yeah, a times cosine of ax. If we know that's the derivative of the sine of ax, then what we're able to get from this is a formula for the antiderivative of a cosine ax. Because the antiderivative here undoes the derivative. So we have an antiderivative of a cosine ax is sine of ax. And we did see a specific example earlier where we found the antiderivative of 4 cosine 4x and we said it was sine 4x. So dividing both sides by a or multiplying by 1 over a, we have 1 over a sine of ax as the antiderivative of cosine ax. Reverse process, with a derivative we would multiply, with the antiderivative we divide, just reversing the process. So, this is a formula that's also on the sheet. So, for example, if you were asked to take the antiderivative of the cosine of 5x, really you should immediately know that that's 1/5 times the sine of 5x. We're not dealing with the constants over here, to be technical, we should have constants, but, we're really just after the formula. So it might seem overwhelming when you look at the formula sheet, but they're showing you the derivatives of functions and then the antiderivatives that result from that derivative, just like we've shown here. The antiderivative of cosine AX is a result from taking the derivative of sine of AX. I would just offer that if that doesn't make sense, then you just have to remember the formulas. Does anyone have any questions on this? So a reminder that the operations are inverses. When we take the derivative of the antiderivative, we get the function back, as in example 2. When we take the antiderivative of a derivative, we know the antiderivative is unique up to a constant, or the derivative is unique up to a constant. So that's kind of the only caveat, is if we take the antiderivative of a derivative, there's going to be some constant involved. But, you know, we're seeing that these operations of derivative and antiderivative do actually undo what the other one has done. Are there any questions at this point? So we're going to talk about a few rules for finding antiderivatives, keeping in mind that they're inverse processes. So we'll just start off with an explicit example. The function is x cubed. The derivative is 3x squared. So remember the rule to take the derivative of a power of x. We said the power comes down, multiplies, and then we take 1 away from the power. So in order to find the antiderivative of something like x cubed, we have to reverse that process of multiplying by the power and subtracting 1. We're completely reversing that. So instead of multiplying and then subtracting from the power, we're first going to add to the power. And then we're going to, instead of multiply by the result, we're going to divide by the result. Or then and, I don't know, then divide. Okay, I hope that makes sense just in a language term from the reverse of the derivative rule. Multiply by the power, subtract 1, antiderivative, add 1, divide by the power. Okay, so that's kind of our justification for the power rule for taking an antiderivative of x to a power. Okay, so notice we start off with x to the power of p. To take its antiderivative, we simply add 1 to the power. So now it's x to the power plus 1 divided by the power plus 1. It's just a direct connection of reversing the derivative rule. It says where p is not -1, because if I have the antiderivative of x to the -1, what is the antiderivative of x to the -1? Do what?
Isn't it natural?
Right. So just notice if we tried to apply this power rule to this, we would say, well, it's x. I'm going to add 1 to the power, and then I'm dividing by the result. So now you're dividing by 0, so it's not a legitimate thing to do. So we won't view, the only power we don't view as a power per se is the -1. We view that as 1 over x, or we view 1 over x as 1 over x. Any other things like that, we always translate it to a power, so we can find the antiderivative using the power rule. But this one is the only exception. Okay, so that's why the power can't be 1, or negative 1. So any questions on that rule? We'll look at some examples. So notice that is the only restriction on that power, is that it's not negative 1. We know that reciprocals of x are powers, they're negative powers. We know that any root is also a power. So anytime you have to integrate, find the antiderivative of things involving roots or reciprocals of x to powers, it's always defaulting back to a power rule. Okay. So what's the antiderivative then of x to the 5th?
X to the 6th over 2.
Say that again, sorry.
X to the 6th over 6 plus c.
X to the 6th over 6 plus c. What do y'all think? So we add 1 to the original power, divide by the result. Go. So here we can check. We take the derivative of x to the 6th over 6th. We should end up with x to the 5th. So hopefully you can see that it does check out. How about the antiderivative of the square root of x?
X to the 3 over 2 over 3 over 2.
Yeah. So the here and now, we're going to think about the root as a power of x. So that's the antiderivative of x to the 1/2. We add 1 to the power and divide by the result. Right over here. So we've got x to the 3/2 over 3/2 plus c, which is
2/3.
yeah, 2/3 x to the 3/2 plus c.
On a test, do you care how we write it? Because there's like so many different ways.
Yeah, honestly,
Between those two.
you should write it like this.
Okay.
I mean, you never want to write put another fraction in the fraction if you can avoid that.
It was just easier to speak that.
Right, yeah, for sure. Okay. Questions on that? Okay. What about the antiderivative of 12 with respect to x?
12x.
Yeah, what's the power here on x? If we're looking at it as a power rule, isn't it x to the 0? X to the 0 is 1. Okay, so we have the antiderivative of the power. Add 1, divide by the result. So we just have 12x plus c. And then maybe you can think about the reverse. What's the derivative of 12x plus a constant? Derivative of 12x is just 12. So if we take the antiderivative of any real number, what would the answer be?
And x plus 6.
Yeah, it's just, we're just adding an x to that number in x plus c. So the antiderivative of the antiderivative of -4 is -4x plus c, so forth. Does anybody have any questions? That's really our first antiderivative rule. There's a couple more that we get in chapter 4. The other rule, like I said, comes in chapter 5 or section 5.5. Two other rules deal with the constant multiple and a sum or a difference. Difference is always included with the sum. So just like when we were taking the derivative with respect to x, if we had a constant, we pulled the constant out, right? The same thing happens with the antiderivative, where the antiderivative with respect to x, it's only affecting the things that have an x. So if we've got a constant multiplied by a function of x, we can take the constant out of the antiderivative process and just multiply it in afterwards. The sum rule, same as the sum rule for a derivative. Basically, the derivative got distributed across sums and differences. The same thing happens with antiderivatives. Okay, so an example, what the power rule then and the constant multiple rule with the sum and difference now allows us to look at how would we find, for instance, the antiderivative of a polynomial. So the antiderivative of 5x cubed plus x squared minus 4x plus 3 with respect to x. So we can find the antiderivative of each term since they're separated with addition or subtraction. So I'm going to write this out just long-handed, I guess. You know, I think after you do a few of these, it doesn't matter if you write it out long-handed or not, because typically we'll just see a function like this and we can immediately write down the antiderivative. I'm just going to put all of this together. So our antiderivative dx part is distributed across the sum and difference. Then for a few of these, we have a constant multiple rule that can be applied. So this, for instance, this 5 can come out and multiply the antiderivative of x cubed. The 4 can come out, multiply the antiderivative of x dx. And I guess the 3 could come out too, if we want to look at it like that. So sometimes you do see the antiderivative of dx. You just have to remember that there's a 1 right there. I mean, that's all that's going on. Okay, now it's just constants times the antiderivatives of powers of x, which we can do. This is 5. This is the antiderivative of x cubed is x to the 4th over 4. Antiderivative of x squared, x cubed over 3. Minus 4 times what's the antiderivative of x? X squared. Over 2 plus 3. What's the antiderivative of 1? X. Okay. Does that make sense? What we've done there? But notice if we did split this up, we would actually get multiple constants from this antiderivative. We would have, I don't know, our first constant. Here we would have our second constant, our third, and our fourth. But really what happens is if we add or subtract all of those constants together, it's still a constant. So we can just put a plus c at the very end. Because all 4 of those constants give us another constant. It's not crucial in when you're doing calculus, I guess. if you have to take a differential equations class, it's super important to keep track of all of your constants. But here, for us, we can just plus C at the very end. So again, you don't have to write all of these steps down. We could just say, well, this is 5 times x to the 4th over 4. This is x cubed over 3, right? We can just kind of do that all in one fell swoop. But what you're doing is you're applying multiple rules at the same time, is really what's happening. Very comparable to when we took a derivative. Okay, how about the antiderivative of this function? What do we do here?
I'll just make square the power rule, so I'd make it x to the negative 2.
Okay, so here's the thing. If we rewrite this as x to the 5th minus 2x cubed plus x squared times x to the negative 2, is that what you mean?
Yeah.
So if we did that, there's nothing wrong with that. It's algebraically sound and valid. However, we're not taking the antiderivative of a power of x anymore because we have this product here.
If you can't distribute it, then
Yeah, so you would definitely need to distribute that in. Right now, there is no formula for the antiderivative of this. And honestly, we don't even talk about how to do that in Calc 1. So if you see a function like that, where you have one function of x times another function of x, or one function of x divided by another function of x, you're not expected to find the antiderivative of that. What it is it's an algebraic simplification problem in disguise. So this is not seen until Calc 2. So if you try to find the antiderivative of a product of two functions, and unless you know how to do that, you're going to be doing it wrong. And I see that a lot on the test. People will write something like this, like that, but then they'll take the antiderivative of each thing. If, on the other hand, this were another plus or a minus there, it would be fine just to take the antiderivative of each term. But it's not. Since it's multiplication, you have to continue simplifying this before we apply a power rule. Is everyone clear on that? Same thing with a quotient. You can't take the antiderivative of a quotient. You have to simplify it first. So then we're just distributing the x to the minus 2 in. So we have x cubed minus 2x plus 1. Now we're just dealing with the antiderivative of a bunch of things added or subtracted together. So honestly, you will not see products of functions or quotients of functions unless it's meant for you to simplify it first. Notice we could have just simplified this from the beginning because this over x squared is really all three of these over x squared. So, I mean, you're really doing the same thing. Oops, minus 2x cubed over x squared plus x squared over x squared. So however you want to approach that, but you do have to simplify before you find the antiderivative. Okay, so the antiderivative of x cubed gives us x to the 4th over 4. Or if you want to write 1/4 x to the 4th, that's fine. What's the antiderivative of minus 2x?
squared.
Right. So remember the constant here is getting pulled out of the antiderivative. So you have the antiderivative of x is x squared over 2. And the antiderivative of 1 is what? X. And then all of those will just have a single constant. And since we can simplify the negative 2 x squared over 2, we'll go ahead and do that. that's our antiderivative. Does that make sense? Do y'all have any questions or comments on this?
I got the single x from the one.
Yeah, this x?
Mhm.
What about it?
What's that from the one?
Yeah, the antiderivative of 1 is x, because that's 1 times x to the
Derivative of
0.
x,
Yeah. Or, yeah, the derivative of x is 1. Okay, how about the antiderivative of 4 root x minus 4 over root x? What do we need to do here?
Can we rewrite those root x's?
Yeah, so we rewrite the root x. So that's 4 times x to the 1/2 minus 4 over x to the 1/2.
Just made it to the negative one half, so cool too.
Okay, yeah, that's what I would recommend. So it's 1 over x to the power for the 4 over root x. So let's make that into 4 times x to the negative 1/2. Okay, and then that way we have sum and difference and constants powers of x. Okay, so the antiderivative of 4x to the 1/2 would be what?
4 times 2 over 3, x to the 2/3,
Yeah.
or
So-
8/3.
So you have the 4, the antiderivative of x to the 1/2 we saw earlier, that's x to the 3/2 over 3/2 if you want to write it like that, but it's really 2/3 x to the 3/2. And then we have minus 4 times the antiderivative now of x to the negative 1/2.
X to the 1/2 over 2.
Yeah. So we add 1 to negative 1/2, we get positive 1/2. So it's x to the positive 1/2 over 1/2. And then we have our plus c. So you should, again, you shouldn't leave it like that. You should simplify your fractions and your constants. So we have 4 times 2/3. So we have 8/3 x to the 3/2. We have minus 4 divided by 1/2, or minus 4 times 2. That's minus 8 x to the 1/2. Let's see. Another thing we could have done is, before we found the antiderivative here, we could have said, well, both of these have a factor of 4, so I could factor this 4 out, and just take this antiderivative. And then multiplied it through by 4. Does that make sense? Do y'all have any questions on this? We actually already did a few of these. The main ones, I think, were the 2 trig functions. So just here as a reminder, if it's not always like a direct relationship. If I know a derivative know it's antiderivative. But it's kind of hard to think in the reverse process, because if you're given, to find the antiderivative of 1 over x, and you don't remember that it's ln of x, really there's no way to start with, oh, let me just try to take the derivative of the ln of x and see what I get, right? Because if you know that, you know the antiderivative, but nonetheless, the process that we looked at where we did this, if we know a derivative, then we know an antiderivative, that's still valid for all of the functions we've seen, really. So we have that ln absolute value of x as the antiderivative of 1 over x, for instance. So this process is sort of null and void if you can't remember the derivatives. But again, if you know the derivative, you know the antiderivative. I think particularly where this process is helpful is when we started looking at find the antiderivative of the cosine of 7x. Something like that is where this process is a little bit more helpful, I think. But again, I'll give you a formula sheet if you want to remember all of it. So let's look at some antiderivatives that require a little bit more effort. So the antiderivative of sine 2x plus cosine 3x. And again, maybe the way you're thinking about this is the antiderivative of sine 2x plus the antiderivative of cosine 3x. So what is the antiderivative of sine 2x?
Negative 1/2 cosine of 2x.
So is it negative 1/2 cosine 2x?
Because it's a derivative of cosine negative sine.
Right. So the derivative, we wouldn't say it's cosine because the derivative of cosine is negative sine, and we don't have negative sine here. So it has to be negative cosine of the same argument, whereas the derivative we would multiply by 2. Here we're going to divide by the 2. So the antiderivative of sine is cosine. Sorry, negative cosine. The derivative of sine is cosine. So you have that that negative that's not there with the derivative. So let me back up then and say that if we know the derivative of cosine is negative sine, then what we know is the antiderivative of negative sine is cosine. Right? If we know the derivative for cosine, we know the antiderivative for negative sine. But multiplying both sides by negative 1, we have negative cosine as the antiderivative of sine. Derivative of sine is cosine, antiderivative of sine is negative cosine. Because again, it comes from the derivative. Okay. How about the antiderivative for cosine 3x?
Cosine or sine 3x plus c.
1/3 sine 3x.
Yeah. Oh, yeah, plus c.
Yeah.
Whole thing.
Do y'all think that's accurate? Does that look right? Derivative of sine 3x is cosine 3x times 3, but then this 1/3 and that times 3 cancel, so we have cosine 3x. And then our constant here. Questions on that? Okay, how about antiderivative of 5 secant squared?
5 tangent.
Yeah. So this 5 is just a constant times that function of x. So the 5 can come out. And we already said the derivative of the secant squared is tangent. So this is 5 tangent. Let's see. What about example 3?
That's just gonna be 1/3 secant 3x.
Okay.
Plus
So we know the derivative. What function do we take the derivative of to get secant tangent? It's the derivative of secant is secant tangent. The arguments are the same, right? It's the secant of 3x. But notice if we just said it's secant 3x, when we take the derivative of secant 3x, we get secant tangent 3x times the derivative of 3x, right? We don't have a, if this 3 were over here, we would be all right. But we don't have a 3 right there. So just like with the derivative, we would multiply by the 3. With the antiderivative, you just divide by the 3. So it has to be 1/3 secant of 3x
plus
plus c. Does that make sense? Maybe looking at it like that, you know, instead of multiplying with derivatives, taking an antiderivative, we're dividing by that. That's especially true when your arguments are linear, because the derivative of any linear function is just the number there. Any questions on that? Okay. We'll start here on Thursday with 1 minus x over x. What do we have to do to this?
Split it.
Yeah, you have to simplify. We don't have a rule for quotients or products of functions. So like I said, if you see an antiderivative that involves a quotient or a product, you've got to simplify that first before you take the antiderivative. See y'all Thursday.